on this computer. So, okay. And first thing first, I guess some logistic first. So if you already kind of like check the campus site, then the campus site will just like forward it to my own website here. So my website is more or less copied from last year. So with little changes, but I guess the materials that I'm going to cover probably will change. I haven't changed the candidate yet. Maybe I will go a little bit more detail like today, like later on, like what I plan to cover. So you have a good idea whether you want to continue to take this class or not. So, and also like, I guess you all now, I guess all of us get used to like doing online classes. So hopefully this is you won't get too upset that most likely we'll have the entire class this semester will be online. And also because of that, like I have changed the kind of my expectation a little bit. Like first of all, these times if you have taken my other classes, like the neurological class and also the computer vision class, you know that I like to have students to give presentations. And this is the first time I teach this information theory. Okay, of course, the title information theory and probabilistic programming that I include this presentation. So, and of course, because of that, like, it looks like I will have like even squeeze the materials a bit more, but I think it would deserve, it's worth it because I always find that like, you guys give really good presentations. Like oftentimes I learn a lot like from the presentations. You just waste some of these materials that I never, I'm never aware of, and it's actually quite interesting. And also, like I think the best way to learn something is like teaching it yourself. So, of course, I cannot afford like I guess I shouldn't say I cannot afford. It would be like a lot of leisure for me if I have you guys present everything like for each of the lecture, but then I probably like you'll get fired eventually. So, but I guess okay, the presentation will be like this if you haven't taken my other course before. So I'm expecting you guys give a 30 minutes presentation on the topics of your choice. I will give more detail like this time. Of course, it should be related to this class. So again, like maybe I start with like what this course is about first. So this is called like information theory and probabilistic programming. So it's a slowly evolving class from an information theory class that I taught over a decade now. So, but over time, like I just incorporated more and more machine learning materials and probabilistic Bayesian influence stuff. And so eventually, so we decided to change the title because it better reflect the materials that we are covering, and also like I think it will attract a little bit more attention. Not attention, but students will probably find more interesting. And so I guess a big influence of this course is a book by Professor Mackay. He already passed away. This is a book that information theory, influence, and learning algorithms. This is free. Like you can get it online. The entire book is like online, so you can just take a look of that. So I think he's trained as a physicist, and then like he have some work in coding theory, and then so on. Like he did lots of inference stuff. So then he combined. He has I forgot it's a Cambridge or Oxford course that like combine information theory and learning, and have a pretty nice textbook. And in terms of the presentation, like one option is because I'm not going to cover like material from this book. Although like I say that the main reference is this book, but I probably won't cover like any chapter of that, like literally I would say. So if there's chapters, especially in the later chapters, they have different interesting subjects, topics, you can pick one of the track and present that. That's totally fine. And I'm actually, in terms of the material, I'm more old school, honestly. Like lots of my information theory materials is by this classic textbook by Kolmogorov and Thomas. There's also the textbook I learned the subject. So in the past that related to information theory, most of the stuff is from this book. But for the rest of the material is scattered. Like for example, for some Bayesian stuff, like scatter, I kind of like obtain, learn the materials from various places. So you can, okay, there's no one particular reference, right? And of course, if you really just want to look, okay, like the books is too much. There are too many books, and I have some set of slides. I only put up the first set of slides here, but I have my entire set of slides from last year as well. Actually, you can go to, say, my last year website. So I didn't make any changes on the slides. So even though, honestly, the material I'm going to cover probably will change a lot. As you see, like I just mentioned, that we need to squeeze the time quite a bit. So it will change. Oh, okay, by the way, like for the Norman folk, I am not sure why they have the class time post in OU learn, 1.OU as like 5 something, 5:50 to 5:30 to 8 something, because this is a pretty large class that with a couple of students from Norman and most of the students from Tulsa. I think we stick with this time, like 3 to 5:50. So if you have any concern, just let me know. So, but I may not even contact the classroom service, because I guess it doesn't matter, because we're going to be online anyway, at least for, I don't know until when. So then I guess we will just like this, stick to this schedule, like every Wednesday, like from 3 to 5:30. So okay, where am I? Okay, that's my poor memory. Again, I have some. So let's see. Like we were here, right? We were here talking about the. Oh, okay. I'm talking about slides. Yeah, slides. So if you go back to go to my other my last year website there. So you have, I have rather comprehensive slides, I would say. So I think it's reasonably clear. So you can just read from the slides. And I think if you don't kind of understand the materials there, just let me know. I can forward you to what kind of where the textbook has. Unfortunately, I don't think it would be too much work again to just change all the slides to add the reference there. But what I'm going to do is instead, like for the part I'm going to discuss today or something like that. And even though like, okay, I put up the slides here, I may not cover this part today actually even. So I will put a pointer like where I exactly cover. And of course, I presumably like just intuitively, I think like you can understand by just listening to the lecture, and you don't really need to read anything, presumably. But if you want to, really get back to read something, I would put a pointer like which part of slides is actually covering the materials, and like the book is covering the materials and so on. The chapter is covering the materials. So okay. So in terms of other logistic things, okay, I will skip this office hour. I will skip this. You can just drop me emails or something like for questions, concerns, and so on. I would say like if it's getting too many emails, I will set up a Piazza site like as last year, because like this class is reasonably big. So, but if it's not too many emails, maybe I can just I will see like what kind of questions you're going to send me. If like lots of questions about the subject, maybe then eventually maybe it's better to set up a Piazza. So I have some of these things that put it up is just because they're required by the university, and we have this mask policy. upper administration recommend us to put it up anyway, and even though we're going to do the class online. And okay, regarding the grading, so it's quite a bit different from last year. So first of all, like I was kind of like recommended to use the grade policy of the university. So therefore, like instead last year I have like A is like from 80 or above, I changed to 90 or above, and so on and so forth. So, but to adjust that, I just give more chance for you guys to get extra credits. So what I'm going to do is okay, first of all, like we still have this. Okay, we have this presentation, this new thing, right? Doesn't have that last year, so we have presentation. And honestly, like presentations, most of you guys should get like pretty high grade. Right? I won't say like 20 of 20s, but maybe at least 15s and or above. And I have some these new things is the extra credits, like 20% of that is like it's kind of quizzes, but it's like really in class participation. So give you incentive to at least actually attend the class. So it's not just log in and then you run away or something like that. So, and I will ask some question occasionally, and then I have just you guys answer, I don't know, yes or no or whatever, or like put some short answer that you can just send through Zoom. So please, okay, send to the host. Sometimes I will connect to more than one. I mean, I will send more than one connection. I mean, I will connect by more than one device because, like, for example, I would like to use my tab to write something, then I may connect also with my tab. So, but when I ask some question, be sure like to send your answer solution. Of course, if it's yes, no question, you can just waste yes or no. But if it's a question that with like something like you need to write a sentence or something, then please send your answer to the host, basically. And so that's think about, I guess, about this grading things, and also like final project we had that last year also, and also I had final project from basically all of my classes, so it's like pretty regular. So we don't have a final exam, but we have this final project. So there will be lots of options that you can work on. So as you can see, like you can do some really classic information theory things like that's totally okay. Or if you want to do some machine learning things, that is fine as well. But I don't want you to just put on like several layers, like how I mean, neural network like just stack, like using like TensorFlow or like PyTorch and then like solve some problems. That I mean, that may not be the best match for this class, because like after all, like AI is not all just about neural networks. Like you see ups and downs. Like even you see neural networks introduced like in 40s, 50s, then like I think it's about that. Like and then 60, 70, like I guess it's like 50, 60, like it has a really a hype there, and then it died down completely. And in 80s, like it came up again, and then with the recent decade, it's also like get really popular. But there are other approaches. Say, for example, like you can consider like 3 approaches that are kind of eternal. Like they are just, it looks like they have something like really meaningful core inside. Like neural network is one of that. The other one is like maybe symbolic model. Like of course, like now many people won't consider that as AI, but it's inside all this expert system, right? And also there's a probabilistic model that we mostly cover in this class. Of course, I won't say I'll cover like really in depth, but like it will give you an introduction. You can get started. For example, like you will know some, okay, at least as an idea, like doing some Bayesian stuff, and then like maybe we will scratch the surface of some graphical models and how do you do influence on a graphical model and so on. And graphical model actually is just the last approach, right? Last group of approaches really, really popular, like before neural networks. In the I mean, like about 2000 to 2010, like actually many people work on like graphical models and so on. So that of course is because of neural networks. Now it's so hot and like, it seems like so powerful that people just forget all this at this moment. But I don't know, like eventually that may be a comeback and that as people converge and merge all these techniques. So therefore it's good to know like different kind of techniques. So and it may not be give you the best result, but maybe eventually you will learn sufficiently, I mean, have sufficient knowledge of that, allow you to maybe combine this with like deep neural network approach and then like get something even better. So therefore, like I would recommend if you do a machine learning something, then try to use a probabilistic model like to solve your problem and for your project. And in terms of the project expectation, there's a kind of like, of course, we'll talk a bit more like later on, but like maybe just give a quick kind of overview here. So this is a what metric that we're going. I'm going to use like. So if you're just submitting, you get 10 out of 40. So if you have a departmental level quality, so what I mean departmental quality is like, you know, like we have all this, and maybe for the Norman folks, not so, I don't know, like, but for the TOSA folks to be quite familiar, like we have this Tuesday meeting every week. Some of them is like really preliminary results that just talking about something, not really study anything. So if you just submit like project like those, then like you will probably get like 20 out of 40. So if you get more serious, like then university level, in the sense that if you have a university workshop, that I don't mean that you win an award or something, but it's like just it looks like the quality of that level, then of those participants and participating projects, then would be like 30 or 40. So if like your work is like kind of like get into like a national, international conference, I don't mean the top conference, I mean just second tier, third tier conference, then you get 40 or 40, so something like that. And another thing, like to just give you another possibility to get some extra credit if you want, hey, at that time, you can also like do a video presentation. So a written report is mandatory, but you can also pre-record a video presentation, and that will give you maximum 10% credit for the entire course. So let me know if you have any question, if anything, I mean, any concern, like so. And so this is about the logistic things. So I guess I'm more or less cover all this logistics and whatever. And of course, we have a midterm. It won't count that much. It will be mostly take home, but it will be, instead of thinking that as a take home exam, I guess it's better to consider that as a just open book exam, because I will probably give you a pretty short amount of time. So you won't have time to search for, because nowadays, if anyone have like 2 or 3 days, like they can solve any problem, like going for, I don't know, whatever site to ask some question and eventually get a solution. That will be, I mean, no one can forbid that. Like this is, so I guess the best way to, and also like fair way and to gauge your understanding of the materials probably is like I don't want to make a closed book also. Like it's, first of all, it's difficult to, under this environment. Another thing is like realistically, when you actually do research, you don't need to remember everything, right? So you just need to know like where you can get that information very quickly. But cheating is not allowed, in the sense that if you just ask question, basically outsource the questions to somewhere else and they answer that. Of course, that should not be, that shouldn't count. And I try to avoid to gauge, I mean, your performance based on that. So therefore, like I will make the take-home exam is reasonably short, in maybe like half a day or like even less than that. So okay, now really get to the real materials. So I guess for whatever reasons we have a pretty big class this year. I honestly I guess maybe one reason is also is I do not have class to choose. So hopefully, even for that reason, you won't be regretted by taking this class after the semester. So, and I think like one problem with the course is like the title. So I don't think this information theory is very attractive. Like the title itself, like I guess it's probably turn off lots of students. That's the reason I put this probabilistic programming. And okay, I forgot. Okay, I when I say probabilistic programming, that's one more thing. So maybe I should explain a little bit this probabilistic programming. So as I mentioned, like this, because okay, this is like related to the maybe I just repeat that. So this is a fancy word, but actually, I don't know. Let me get to a list of them. Yeah, this is a fancy word, but it's basically like just you think of like, okay, I have maybe do some Bayesian inference or like graphical model and so on. So just like you have like packages to write low lateral quickly, maybe PyTorch, TensorFlow. So presumably like to make things efficient, like people also, okay, I think it's pretty loud. So people also like develop lots of these languages and packages to do this inference very quickly. So I didn't actually look into many of this. I play with Pyro. Pyro is by Uber. Let's see, where's Pyro? Yeah, Pyro is Uber. It's based on PyTorch a little bit like last year. I forgot most of that like now. And also like play with Cursor, like not exactly Cursor, but like there's a Angelica, like this Angelica Cursor. I actually try to learn Cursor just because I want to learn Angelica, but eventually I find the author himself, like he was a professor in Oxford and then moved to like UBC, University of British Columbia, and he gave it up also. Like he worked on a new project not based on Cursor, but like based on Python. So then, but anyway, like he has a class, like I think the professor's name is like Frank Wood. He has a class on like probabilistic programming, but it's more like from the perspective of a developer is trying to develop a probabilistic programming language. So of course, like for us, it's very different. This is an introductory course and mixed with some information theory and so on. So we the goal here is like trying to understand like from the user perspective. So they have some API. You're supposed to learn how to do some simple Bayesian inference, like how and like what's variational inference and so on, so that like you will understand what's the API supposed to mean. So therefore, like the goal here, like as I said, like you will be a complete user. So as I said, like I just mentioned, like for the presentation, one option I said that like, you can present, say, a chapter from this book, right, by Professor Mackay. And another option can be like you can look into like some of this library. I guess like this also the same thing when I teach the neurolateral class. I will just suggest students to look into maybe TensorFlow and PyTorch and try to present that, like so that like everyone will understand. So And you can also like look into some of the packages, like packages that you find that most interest you. Maybe because of the background language, maybe I know some people may be really in love of like some languages. I only like kind of like use really general language, right? Like Python and so on. Maybe someone is really like Haskell or like so, and like maybe like Scala or something. So it's all up to you. Maybe I think there's a web PP or something. Web web PPL, yeah. Or maybe you want to use even like use a web PPL because it's based on JavaScript, maybe. So and I guess it's like up to your choice. Like if you find some of these languages is more interesting to you, then maybe you can look into more like some of these packages. And you can present one of those. So, and that's something about okay. Well, I like to talk about probabilistic programming. Okay, and okay, I guess back to the material again. Like, so the class, like information theory, maybe a little bit background of information theory. Maybe lots of you guys probably know a little bit about that already. So maybe from some communication course, I mean telecommunication courses, that you can say that information theory is like single-handedly created by Kos Shalom, and he was working in AT&T and published a couple papers, and he made up some what groundbreaking idea at that time. Like before that, like no one have thought that way. For example, like when we think of a channel, or maybe I start with information, maybe because like this is information theory. Right? The first thing is say, how do we define information? Like what do we mean by information? So he gave a rather abstract definition there. So he doesn't say, okay, whether, of course, everything can be information, right? I have this piece of text as information. I have an image as an information. I have a video as information. So we don't exactly care about like what kind of format of that information have. So if we care about different formats, that would become a data science class. But we go one higher level of abstraction. Basically, we just think of, okay, we would say anything can be information. But one thing I would be interested in would be then like, how do I compare information? So if I have a piece of text and I have an image, so which one have more information? So I guess like now is, and maybe like I can jump ahead, like two very important film by Shannon is like the, maybe I have this, is the source coding theorem and also the channel coding theorem. So basically the source coding theorem is saying that, okay, for whatever piece of information, I have a quantity, okay, eventually we call it entropy. And this basically measures the amount of content of information of that piece of information. And it shows that like, as long as we store that piece of information with more storage larger than the entropy, basically you can think of the entropy of that piece of information is like the minimum size or the maximum compression you can make to squeeze that piece of information into. So if you squeeze it more than, smaller than the entropy, then you will be unable to recover the original message. So you won't be able to recover the original information. So whatever recover will be lost, lossy. So for example, if I have an image, if I will say like, I compute the absolute entropy of that image is like 100 kilobytes. So if I squeeze it more than 100 kilobytes, then whatever I recovered will be lossy. So there must be some loss in the image, like that. Maybe there's a pixel is off, maybe the intensity is off a little bit here and there. And another idea is like the channel coding theorem. It's basically saying, like, of course, this is related to communication engineering. M. Shannon is a communication engineer, of course. And basically, we have a channel. We say that like every channel, based on the characteristic of the channel, will have a capacity for that channel. And we cannot pass, for each use of the channel, we cannot pass more information than the capacity of the channel. Actually, this idea seems like pretty, I mean, like now it doesn't look groundbreaking at all. It's like looks pretty natural. But before Shannon, many people believe that like you cannot have lossless communications through a noisy channel. Because actually at that time, like, many people is thinking of like analog signal. At that time, it's most of these circuits and everything is analog. So people think of, okay, you have something noise, how can you remove that noise? There's no way you can remove the noise, right? So therefore, like whenever you pass through something noisy, you always end up something noisy. So you cannot remove the noise, therefore you cannot get any message passing through a channel without getting any loss. So that was the consensus at that time. So therefore, like now looking back, like it looks completely lateral, but actually it was quite groundbreaking. So we will get into some of this, like actually more detail like later on. So, but probably not as detailed as I offered last year because I want to save some time. So for example, for source coding theorem, I won't get into like all this code, like maybe SFE code and so on. And also I probably won't cover collapse inequality and so on. And I won't talk about optimization anymore. So I will give a so with skipping that will allow me to give some won't allow me to give a very rigorous proof of the source coding theorem, but still I can give a intuitive explanation why source coding theorem work or like has to make sense. So okay, maybe now I just want to try whether you guys are still here. It's a little bit quiz time here. Okay, I also like I guess for this one thing, for my quizzes or like participation, whatever, I want to make it like that's incentive for you guys to be just attentive. Like it doesn't matter you gave a wrong answer. So for example, if the question is 1 point, then even you give a wrong answer, you get like 0.5 points. If of course if you don't give any answer, then you don't get any point. So let me let's say, okay, I just want to get some feedback here. So what do you guys think if I have, maybe I should write it down so then so you can see my screen also here. Let's see. So let's see, I have a question like this, like let's say pi, all of you guys know pi, right? So how much information do we have for pi? So pi in terms of like, if maybe I move back. So assuming that I want to get the infinite precision of pi, so how much information do we have for pi? So maybe I give you like a minute or two like to think about it, like what do you guys think? So is that clear? Like, if you need any, if you want to ask a question for me to clarify the question, like.
Yes, I want to.
Let me know.
I want to get this clarification, but what do you mean by getting infinite precision? Because we are never going to get that. So, like getting infinite precision, what does it mean?
Okay, someone said that the mic is a very mic volume. Okay, I didn't know that. Wait a sec. Why I think the mic is pretty. I have someone I said the mic volume is. So do you guys still have problem with the mic?
Now it's good.
I didn't check the chat earlier. Sorry about that. I think Zoom is pretty weird. I think I set the mic volume to maximum already, but it doesn't do any help.
I can hear.
There's an automatic entrance. Let's see, I remove the automatic. Does it sound louder now? I don't know. Okay, so I see many of you guys have answered. Let's see. So I guess I will just, okay, I assume that you guys, okay, for the rest who didn't answer, I will just, you guys just skip this question. So that is, okay, that's a tricky question, honestly, because it really depends on, okay, from our discussion, you are right. Actually, most of you guys are right. That would be like infinite amount of information, because like if you think of like, okay, I have pi. Let's say the easiest things that you may check, like even do it at home. They say, okay, let me generate pi with like maybe use with some software like with like 10,000 precision, and then try to compress it. You're using maybe zip, and if like and then maybe from 10,000 you from 10,000 precision you change to 100,000 precisions and compress with zip again. And you just look at the trend, like whether like you will just settle. Like, of course, I don't expect we will settle. Basically, like, you maybe you can able to compress the number a little bit, but as the precision goes, the size of the you basically you cannot compress that. But as I say, it's a tricky question. Like that's the thing. Like I want to mention, but actually we won't go further like in the future. It's like, okay, from I guess like from Shannon's perspective, this is infinite. You guys are right. And actually, I will mention one thing like long as this from Kolmogorov. So they have this Kolmogorov capacity, or this known as the algorithmic information theory. That's in theoretical computer science. So Kolmogorov capacity has something very different definition. Basically, it defines the amount of information of something as the minimum size. Okay, maybe I just put it down. Minimum. I don't know how to spell minimum size of program to generate the piece of information. So in that sense, because you know that we can generate pi like with some program, right? For example, like we know the pi square over 6 is equal to 1 plus 1 over 4. I mean, like, you know, something like that, right? Pi square over 6 is something like 1 plus 1 over 4 plus 1 over 9 plus 1 over 25 and so on and so forth. So theoretically, like you can write a program, just say do this infinite sum and go back and do the square root and find pi like with infinite precision. And that program will be finite size. So therefore, from Kolmogorov's perspective, the amount of information for pi is finite. But from Shanlon's perspective, like how we think of Shanlon's perspective, actually I didn't go into detail there yet, but this is like the perspective is a probabilistic for it. So we consider everything as probability basically. And of course, you have if you look at the digit of this pi, if from the probability's perspective, it doesn't look like that we can, based on like previous digits or previous number of digits, we can predict the next digits. For example, like if we are able to just based on probability to see that like given the last 10 digits, I know the next digit is going to be 1, 2, or 3, 4, something like that. Then basically that would be like a finite model, like probabilistic model to generate pi. But here we do not. I'm not sure I'm here. So what I mean is like if you can have a probability model, something like, for example, like I have a digit, let's say pi is equal to like D0, D1, D2, something like that, right? Dn. So maybe if I have like Pdn given my last digit, n minus 1, dn minus 2, and so on and so forth. And somehow, like if I have this probability very close to be a delta function, what I mean is like given this probability would be like dn, for example, I have dn is equal to v, is close to 1. So that means that I can precisely predict what is dn is, right? Given like whatever here from this guy here, from just like the previous digits. If I have a model like that, then it will be very much compressible from Shanlon's perspective, because like given the last digits there, I can already tell that what is the next digit, right? So I don't need any extra information to store. I mean, I don't need to store any extra information to realize what will be the next digit there. Okay, I guess I'm jumping ahead, but I just want to give a major difference here. It's like, you may not understand everything I said here, but it's okay because I will get more detail in the future. But what I want to emphasize here is that like Shanlon, of course, like many of us like are electrical engineer, so we typically see things like from the probabilistic perspective. So everything is probabilistic. So and the Shanlon information theory is like based on, it's basically you can think of like information theory really is a applied probability, and it's like yeah, and it's quite different from the theoretical computer science and mathematicians like maybe Kolmogorov like think of a very abstract way, so even more theoretical than like the information theory. But in the sense like I don't know, like I guess the problem is like the Kolmogorov complexity is like philosophically it's very nice, but in practice it doesn't go anywhere. It's like basically that, and I don't know like how we can use this idea to I mean kind of help us to develop or like design any new system that can solve any practical problem. So okay, that's probably like my last time we talk about Kolmogorov complexity, but I think it's good to mention here. So if like you come across like someone to ask you about algorithmic information theory, then at least you know they are actually referring to different things other than like the information theory in electrical engineering or communication engineering. So, okay. And that's, I guess I will get a little bit more detail now. And hopefully, like, you guys will find these materials like not totally dry, and like some of this stuff will be interesting. And one thing I want to emphasize also is, I know many people don't like theory class, but I want to say like these materials can be much more useful than you thought, because it's not just like give you more insight, intuition, like in solving some of the problems, but also like what you're going to learn now, I can assure you that like it can still be relevant like 2 decades later on, because I basically learned these materials about more than 2 decades now, like a little bit more than 2 decades ago. And I also remember like 2 decades ago what I was learning. I was learning Perl. I'm not sure how many of you know Perl. Any of you, like maybe you can raise your hand if you know what I'm talking about. No one at all. So let me I try to spell that. Perl. So okay, anyone? Still no one know anything? Maybe you can raise your hand, or like if you don't know, you can maybe say no. Okay, someone say okay, yeah. Someone show at least heard of that. So it's a scripting language.
Yeah.
That was quite popular in early 2000 or like before that. I was writing some bash file like bash like in Unix. So like Linux is still was still not very user friendly. So I used bash white script, like maybe C# even. And but I because Linux is was not user friendly, I still use a lot of Windows, and I want to have my script to be portable. Then I try to learn some Perl, that can be run in Windows. And of course, like 2 decades later on, many of you even don't know what is Perl, and who knows? Like 2 decades later on, maybe Python will maybe disappear as well. So, but 2 decades earlier, I still learned this thing, and it's totally relevant. So that, okay, I guess like that's a partial proof that these things is more everlasting than some of these like packages, languages that people use. So okay, let's see. I guess I will get into let's see what I. So I have like talk about this website, logistic, quiz, presentation. I have some introduction on IT also. So for this course overview syllabus, I don't know whether I need to go for all this. My current plan, maybe I just quickly mention this. Today I will talk about some probability, like some review. I guess most of you guys is really review, but I hope it's still interesting, because I think I will talk about a Monty Hall puzzle that some of you maybe heard of that before. I don't know, like maybe raise your hand if heard of that before, but don't ruin the other guys. They may enjoy that. So okay, like someone heard of that. So this is a very interesting puzzle, but I will talk about that later on. So I think like but I will just give a probability overview and so on and so forth. Then I won't talk about like formal probability model. I talked about that last time, but I don't know, I don't know, maybe, yeah, because I don't remember that myself. Every time I need to read it again, I guess probably if you don't remember something, maybe it's not actually that useful. So and after that, I think like I'll skip. Okay, I won't go into this. Like for the moment, I will talk about that, but I will skip all this. But instead, I will go all the way to law of large number. And with that, like, we'll talk about some typical sequences. It's an important concept in information theory. And this allows us to give a not rigorous proof, but like a very intuitive argument why source coding theorem works. And then afterward, I guess I will I will kind of
Hello,
digress a
Professor.
little bit like from information theory and go back to talk about this mathematical map and so on. And also like we need to talk about some of this distribution. It may be boring, but it's kind of useful, right? So we'll look at different distributions and so on. So last time I pushed it till the very end. I guess I should put it up earlier because when you look at different packages, like you're expected to know this. Like you don't need to know it by heart, but at least like you don't get scared. Or you see that before and you know, okay, that's okay. They mean that. Right? That's nothing really so special. So I hope to give you at least that impression. So then,
Dr. Chen, can I ask a question?
Or maybe I should. Okay, maybe I shouldn't do that first. Maybe I should give some information measure first. I need to, because one thing I made very importantly, besides the source and channel coding theorem, where we have these languages of information theory, it's just like some of this information, mutual information, and so on. And these languages are useful, not just in this communication engineering, but also like you see that like in machine learning and so on. And for example, quantum entropies, you kept seeing that, or like K divergence. And I think it's very nice to look at like where they come from and from a different perspective. So I guess I will talk about that first, and then I will talk about this. So I probably by that time maybe like half of the course or something. Then you guys may have some presentations. I don't know how many of you guys are dropping this course, but it looks like if we have a reasonable, if we are not many people dropping, then probably we still have like, we'll occupy 3 classes, maybe like for presentations. Then after that, I probably will talk about channel coding, but probably not as in depth as last time. I think it's another very nice idea, also like an example to use some of the idea. And I would like to talk about method of type. This is another very interesting idea in information theory. And then we'll see. Then for time allow, maybe we'll go deeper into some graphical model like Gaussian process and so on and so forth. So that's my current plan at this moment. Okay, now okay, we get to the core materials now. I may use a pack, maybe easier. Let me pick my iPad. Let me first connect. Let's see. Oops, I don't know why it's so way a little bit. So I have this done up there. Also, oops, why is not connecting? Okay, I need to kill this first. Okay. Let's see, I need to make myself host by other. Oh, actually, another thing, say, I really like occasionally I really want you guys to explain stuff if you can. Like for example, for some of the derivation, if like someone can is willing to derive it in class, then I can give extra credit for that also. But of course, like that the problem is with Zoom now, then it's a bit I mean, like you guys need to have like tools like for you to derive things. Like if you just type something as like what I did here, of course it's possible, but it's like only okay for like doing some very simple derivation, I guess. So I would suggest that I don't know how many of you guys have any writing devices. Like, okay, maybe I just get a poll. Like, how many of you guys have some tools allow you to present stuff online using writing? Like you can write on the screen. It can be like either your laptop or you have a tab that you can write on screen. Or okay, some of you guys have that. I will, because under these circumstances, I will highly suggest you guys to invest on that. Like I recently bought something. Okay, of course there's several options. It depends on whether you want to invest a lot on that, or like, for example, you can totally buy an iPad or something that what I do, like, but it's kind of expensive solution. Or if you buy another next laptop, you're prepared to upgrade a laptop, try to look for a laptop with a stylus. A much cheaper option is like you can get something like, for example, like I just bought something called this Expand here. It's kind of okay. I mean, it's like quite cheap, like $40. So I cannot. Okay, this is what I'm using it now. So let me I open the Zoom notes just to why am I so slow? So I'm writing it now. So it's not exactly my name. So not exactly very. I mean, it's not the easiest things to use, but it's reasonable. I mean, if you just try to do some presentation or like online teaching like that, that's doable. So I guess you guys can take that as one possible option as well. So because I guess these online things will last for quite some time, and I think it's a good investment. But you can think of like different possibilities, different options, and this having with two sides that would be very useful. So that when you have a kind of online meetings like this, then you can present something more easily when you need to explain something using a pen and paper. So okay, let me close this. I don't need this anymore. So let me go back to, I have this and I have that. So I don't think I want to connect with whiteboard. So let me. So okay, we'll just keep a quick review like for probability. So let's see. I guess let me also, I have some notes. I guess I probably want to take it, just make sure I don't miss something that I want to talk about. Okay. Okay. Exactly. Just make sure I put up the list so that I can see you guys. So, okay, we talk about probability. So start with something very simple, right? So I guess this is, of course, I assume like you guys have some background on that. I'm not sure like how much you remember, how much you don't remember. Probably you guys should be quite familiar with everything I'm going to talk about. So, but let's say like start with like we talk about probabilities, like we have some random event. So something is probabilistic, and I guess okay. Okay, I guess I can't. I see you raise your hand, but maybe I will do. It's like maybe I should just lower your hand now. So I just want to make sure that if you guys have questions again, just raise your hand again. Maybe I will clear your response for the moment. So that okay. So think of like we have some random process. Okay, make up something random. So random in the sense that each time it can have different outcome, right? So we have some event can be random and can have different outcome. So a random variable is just each time you can have different outcome, right? I have a random variable, and the outcome of the random variable can be numerical or it can be non-numerical, can be categorical. For example, like a classic example is like maybe I have a jar and I have like different number, have balls like inside with different colors. Then maybe I try to kind of pick up a ball from the jar, like I have a hand, so I just go inside and grab a ball. Like, of course, I cannot see the jar inside, and then that will be a random variable. Right? Each time I pick up the ball, like it can have different colors. So in that case, the outcome of the random variable will be like different colors. It can be red, green, yellow, and so on. And of course, like we can also have like random variables and numerical, and also like even when we have my random variable are categorical, I can label that as number, then it becomes numerical as well. So okay, this is like the most simple concept. So then like probability would be like just describe like how likely that an outcome will occur. So for example, like in this case, I have two red balls and one green, one yellow here. So if I just blindly pick up a ball, like then the probability of getting a red then will be just like 4 out of 2, right? Or 2 out of 4. Let's see. Yeah, 2 out of 4, right? Or 1/2. And I can like probability of like getting green and yellow is both like equal to 1/4 in this case, right? So this is the probability. So something is very natural, right? And now then, okay, then this is a super fast introduction of just probability. Then the next thing I need to talk about the distribution. Like we have this PDF and also PMF, this probability mass function. And this probability density function. And so this PMF is just basically the function that lists out all the probabilities of all the outcomes. So for example, like in this case, in this example here, I can have the PMF. I can plot the PMF as like I have different colors here. Like I have red is 1/2 way, and then yellow is like 1/4, and then green is like 1/4. Then this distribution thing is my probability mass function. And and maybe another example, let's say if I have a dice, like a dice that have 6 outcomes, I have 1 to 6 way. If it's a fair dice, then the probability will be uniform. I have 1, 2, 3, 4, 5, 6 of them the same. And then for one thing is we want the probability to add up to 1. So therefore, like each of these should equal to 1/6. Actually, I don't even remember to mention that, right? So of course, the probability, when we add up all the probabilities, it should be equal to 1, because if we say like what's the probability to get any of this outcome, will be the sum of all these probabilities, right? And the probability of getting all of the outcomes, by definition, we say 1 is like it will happen. So therefore, like when we add up all the probabilities, it should add up to 1. And also, like the probability is supposed to be non-zero. Oh, sorry, not non-zero. So it's supposed to be non-negative. If it's negative, it's just undefined. So therefore, like my p here, the probability has to be big, less than equal to 0 and bigger than equal to 1. If this is discrete, okay. This I need to emphasize that. So the probability itself should be like from 0 to 1. And so for PDF, like let's say the probability density function, this is for the case when you have a continuous random variable. Continuous, when the random variable is continuous. For example, I can have a continuous random variable. Let's say I have a random variable x. It can take uniformly from 0 to 1. So, and uniformly in the sense the probability is all the same. Then I would draw the PDF as this. So know that like when I have a continuous random variable, then I cannot really define something like, let's say x is continuous, then I cannot ask something like what's the probability x is equal to 0.5. It will be just always 0, right? Because if this is continuous, like you can have infinite precision that I can have like 0.50001 is still not 0.5, right? And so because like this is like have infinite amount of combination, if you split it among these infinite combinations, and each of these possible outcome to be exactly equal to a particular values has to be equal to 0. So therefore, the only way we can describe the probability, I mean, the statistics in this case is just saying like what's the probability that within certain range. So we say the probability of x between, let's say, like x1 and x2. We can ask this question. And in general, this should be non-zero. This should be like bigger than 0. And this is like specified by the PDF. So for example, in this case, I can have like x1 here is like 0.4, let's say. And then I have x2 is like 0.6 here. Then this probability will be simply the area underneath this PDF. This is a PDF again. So then in this case, it will be just equal to 0.2, right? So this is just, okay, let me write. So probability for x is 0.4 and 0.6 will be just equal to 0.2. So this is, again, this is uniform in this case. So any questions? I assume like this, you all know that, but maybe you forget it. But this is a PDF, PFF. Remember that like distribution is just, I don't know, just list out all the probabilities. It's distribution, and for PMF, like you deal with like discrete random variables, and PDF you deal with like continuous random variable. And because of continuous, you cannot really talk about probability at a particular point, but you can only talk about a range. And of course, in this case,
Professor Chang,
because I define something like that, if I ask what's the probability that X
Dr. Chang,
from like minus infinity to plus infinity, it has to be equal to 1, right? So that means that the area underneath the PDF has to be equal to 1. So therefore, actually, the height here is actually equal to 1. So because the width here is 1, the height should also be 1. So 1 times 1 is equal to 1. So the area is equal to 1.
Dr. Chang?
And so let's see, we talk about PDF, PMF. Okay. Then the next thing is I cannot hear you. So anyone say something? Oh, you need to unmute first. Let's see. If you unmute and try to talk, I guess I should be able to hear.
Yes, can you hear me now?
Maybe my volume is not. Can you say something again?
I am unmute.
Yes.
Okay, so I wanted to ask, you have written probability of 0.4 up till 0.8 is 0.6. Is this just a random number?
Oh,
or you
okay. Yeah, it's a typo. I'm sorry. Yes.
Oh, okay.
Oh, thank you. Yeah. So, okay. Thank you so much for catching that. So, yeah, I tend to make lots of mistakes. So please just catch me. So let's see. We kind of give this review and PDF, PMF. Okay, next thing I should mention expectation. So when we have expectation, first maybe consider discrete random variable first. So if I have the PMF, let's say, oh, by the way, like in many, probability textbook or like stochastic variable textbook, they typically use PDF like with like F something, like that's PDF, like FX or something like, and PMF maybe PX. So here I'm not going to, actually I just also like follow the convention in COFA, like I'm not going to distinguish like P and F here. So I most likely I will just use P for everything. So, but even you see like PX, it doesn't necessarily means that like the X has to be a discrete random variables. It may also be continuous as well. Let's see. So okay, expectation, yeah, expectation. So if I have a discrete random variable, let's say I have discrete random variable X, let's say, and I have the PMF is like PX. This is the PMF here. This is the PMF. Now, if I think of like X, if I have a function, a deterministic function, let's say I call F. Okay, F is a function. F map X into something else. So maybe actually, maybe I say in a more, or maybe map to some number, let's say. Then I can have like Fx now is a random variable, right? So X is a random variable, Fx is a random variable, it's actually a real random variable, so it's a numerical random variable. And I can define the expectation of Fx will be just the weighted sum of Fx by the probability. So will be just equal to Fx Px sum over X. So X by for all the, this is basically the alphabet. So maybe I shouldn't have S, right? I don't know. Alphabet or alphabets. I don't know. My English is bad. So yes.
Okay. What is f in here? I didn't notice.
F
What?
is just any function, right? Any function. So you think, okay, let me give a concrete example. Let's say my x here is like this jar here. So I have x is this jar, right? So this jar outcome can get like red, green, and yellow. And then I have f is basically mapping this different color into number. So let's say, for example, I have f red is equal to 1, and f, oops, that's a, maybe I just write like this, f. So red yellow is equal to 2, like red green is equal to 3, I say. So it's just a mapping, right? And then so then fx will be a random variable, right? So x is basically what color you obtain after you grab from this jar here. Then fx is just mapping the color into a number. So for example, like when I pull from this jar, I get a red ball. So this time I will get 1. Basically, my fx then is 1. If I kind of like draw from this jar to get a green one, then I will get fx in this case is equal to 3. So is that clear now? So yes.
This expected value will depend on how we define our function f. So if I change the mapping of the colors, then my expected value will change.
Yes. This expectation will be depend on f. So expectation here depend on f. You have different function, then you have different expectation. For example, if I change this f, instead of map to 1, 2, 3, I map to like 2, 4, 6, then my expectation will be double.
Okay, thank you.
Yes. So yes. So maybe I just complete this numerical value, then maybe you guys will get more kind of like, I mean, this is a little bit more clear. So then in this case, then what will be that? It will be like f my red way f, okay, I guess like this, times the probability is a 1/2, and then I f, this is a 1/4, this half 1/4. This is red, so this is yellow, maybe this is green, and then so therefore like the expectation therefore will be just equal to like 1/2 plus 2/4 plus 3/4. So therefore if I put 7/4, I think. So that is expectation. So hopefully it's clear. And I can do the same thing for continuous random variable, right? So if I have continuous random variable, I can also have define a completely similar manner for the expectation. So for example, I can have also a function, but let's say this time, if my random variable here is a continuous, then I will have I'm sorry, I just want to get some water. So I will have let's say expectation of fx. So actually, for one thing, like maybe I should emphasize, I try to be careful, but sometimes I may occasionally have typo. You see that like I make a difference like when I write expectation fx and when I sum over x here. So this I use uppercase, this here I use lowercase. So this is a convention that many people use in probability, stochastic random variable and information theory and so on. And this just makes the distinction that it become clear, whenever I use uppercase, I mean that this is a random variable. So it's not a constant, it's a random variable. And whenever I use a small lowercase there, I mean this, I'm drawing a particular instance from that random variable. So therefore, when I write small x here, I mean that one is actually a deterministic thing. Okay, hopefully I didn't say something that even make you more confusing, but okay, just a quick word. Basically, that what I want to say is whenever we write in uppercase, we mean it's a random variable. When we write a smaller case, lowercase, it means that it's a instance of the random variable. That's we draw a particular, we did a particular sample. We did a sampling and get a particular instance of that random variable. So okay, let's go back to this continuous case here. I have expectation fx will be equal to will be defined as fx px. Now because here is a continuous random variable, I actually have integral instead. I have dx, something like that. So because I have PDF, remember that when I PDF, what the probability is not exactly equal to px, but instead the probability is actually the area underneath this thing here. So therefore the area underneath is I need to take the integral of that to get the area underneath. And that's the expectation. And one thing for both my discrete and continuous case, note that expectation is a linear operation. So for example, if I have expectation of x plus y, let's say, or ax plus by, where a, b are constant and xy a random variable, then this is a linear operation. So therefore I can write it as expectation ax plus expectation by, right? And this is equal to expectation a expectation x plus b expectation y. Yeah. So now with the expectation is defined, then when we talk about average or mean, it's a very simple thing, right? Then when we say whatever the mean of some random variable and the numerical random variable, let's say I have x here, I don't care whether it's continuous or discrete, but as long as this is a numerical random variable, then the mean or the average is defined. It's just equal to the mean of x is just equal to the expectation of x. Right? It's just equal, for example, for the discrete case, it's just equal to x px sum over x, something like that. Okay. And maybe I just clean out some space here, or let's see what should I do. Should I clean out some space, or you say maybe I just so
I have a question.
Yes.
So what is the expectation of the random variable y? How can it calculate the expectation value of the EY?
Oh, okay. This here is just a general case. I didn't define what's y yet here. So, but here is for any random variable, x and y, both of them are numerical random variables. So basically, they are random variables that have outcomes is a number. So if that's the case, then it doesn't matter what this ax plus by, what are they? It doesn't matter what are they exactly. I mean, this equation will always satisfy. So basically, I have expectation ax plus by will be equal to a expectation x plus b expectation y. So this is true just because our definition here is linear. So maybe I can give one more step here. Maybe let's just look at the discrete.
The probability density px is must be the pxy. It must be two-dimensional, the function. I'm not sure. So still, I don't understand. What's the then difference between ex and expectation of x and y? It's supposed to be two different random variables, right?
Yes, there are two different random variables. Okay, I guess this is another things that I guess I forgot to mention this sometimes this shorthand notation, I guess but of course this px when I have a y, there should be a different p here, but it's understood when I write px here, this px is actually a function of depends on x, something like that. So let me elaborate that. I just maybe look at just expectation x plus y, let's say. And let's say x, I have a probability distribution of px, right? And this have a probability distribution of py here. And then so from the definition here, I have this is x plus y. Let's see, where is that? X. Yes, I guess I can go x plus let's see, small x plus y sum over. Okay, so there's some click there. I hope that you can hear me clearly. I don't know. And p xy, right? Sum over xy. So I think you're right. I need to look at the joint probability, right? So I have p xy, something like that, right? So, but then because this sum here is linear, right? So then I can have equal to xy, x pxy, and xy here plus xy, y pxy, xy here. Now then I realized that I should also mention marginal probability, right? So when I have a joint probability, pxy, xy, if I marginalize that, I sum over just one random variable, sum over x. So what do we get? I will basically get pyy, right? Do you agree with that?
Yes.
Yes. So therefore, I look at this this sum here does not depend on. I mean, this y here does not depend on x, right? So my sum x here can just go inside. So it means that I can write it as I mean, this guy. Let me just write one more step. So, oops. So this is sum over the first term. I say I have a sum over x. I have x here, but my sum y can get inside. So I have pxy, xy here. Then this guy will just get pxxy. And similarly, I have this other guy is y, p, y here. So therefore, like this is actually just expectation of X, and this is expectation of Y. Okay, is that clear? So
yeah.
Yes.
So this the linear condition is not always true, right? It's only the probability density is the joint function, right?
No, actually, this is actually always true. Like you basically, this is always true. Like you can try to show that. Like this is like I can put in whatever like A, B here also, it doesn't change anything because I have A, B here, right? Then I have A, B here. Then my A, B can pull out here, A, B here. So you can see that like, because as long as this is true, like because we have the joint probability, if we marginalize one of the random variable is equal to the marginal probability. So then you see this is actually, this already a proof of that, right? Right? This is actually a proof of this guy. Yeah,
I got it.
So therefore, like it's always true actually. Yeah.
Okay. Thank you.
Yeah, sure. Okay. Let's see. So this is for expectation. Okay, next thing. So with expectation, then average, we just mentioned average, where average is just, it's just its expectation. If I have the mean of something, it's just expectation. Maybe I give an example. Let's say if I have something like, maybe I put some numerical things, like maybe maybe I have something like that. So this is 1, 2, 3, 4, and this is like, let's say 0.4, 0.3, 0.2, and 0.1. So then the average will be just equal to, it's just equal to the expectation, will be like 0.4 times 1 plus 0.3 times 2. Oops. Plus 0.2 times 3 plus 0.1 times 4, right? So then it's, I don't know what's that, like 0.4 plus 0.6 plus 0.6 plus 0.4. So it's equal to 2. Yeah, something like. That's the mean for that. And we also have the variance, right? So also mention the variance. So for a numerical random variable, again, no, it doesn't matter, it's discrete of continuous. The variance of a random variable is equal to the expectation of X minus expectation of X. That's basically minus the mean, and take the square of that. And this is the variance, right? So the idea is like, I want to see like for the X, like how it different from the mean. So how it differ from the mean, and then I just square over that and see, okay, basically you can see if the distribution is more spread out, then the variance, like this variance will be higher. So if it's sharper, then the variance will be lower. And I guess like this, you should also see, using like what we described, like the linear property of the variance, we can show this very useful kind of equality. Basically, I have the variance of X is also equal to expectation of X squared minus expectation of X squared, something like that. So so this we can easily show them. Maybe I show this anyway. So this one, I have expectation. Okay, I can take square of that. Is like I got X squared minus 2 expectation of X, right, times X plus expectation of X squared. Okay, here I just expanding this square root. So I mean expanding this square, I didn't do anything. But okay, what's the next step? So the next thing is I can use the linear property of expectation, right? So I can get inside each of these. I have, this is equal to expectation X squared minus expectation 2 expectation X times X plus expectation expectation of X square here. So now know that like when you have expectation of X, X itself is a random variable, but if you take the expectation, after you take in the expectation, it's already not a random variable, it's deterministic. Like in this case, for this distribution, after I take the expectation that's getting the mean there, it's just equal to a value 2. So therefore, this is a constant. So if you take the expectation of a constant, it's just itself, right? So therefore, this is actually just equal to expectation of X squared. And for this guy here, therefore, like this whole thing is here is just a constant, right? I can pull it out. So therefore, it's equal to expectation of X and expectation of X here, right? So therefore, I get 2 expectation of X squared. So therefore, like, this thing is just expectation of X squared minus expectation of X squared. So okay, that's mean and variance. Okay, I guess I will pause here like for 5 minutes or so, like as a break or something. But how about this? Like again, a small super stupid simple exercise. Like, can you compute the variance for this distribution? So the mean is equal to 2. What's the variance? Like, can you? So it's a quiz 2. Variance of X. Here, this is the X. This is X. So X with like with 0.4 probability to be 1, 0.3 probability to be 2, and 0.2 probability to be 3, and 0.1 probability to be 4. So maybe like can you compute that? Like we can come back like in, I don't know, 10 minutes or something later. So maybe 450. Like we'll compare 450. And you can like again like send the your answer like to the host. Please send the answer to the host. Yeah. You can just like write down like what's the numerical value directly. Actually, you can skip the step, or if you want, you can write the step as well. Yeah. So I'll just get some water and come back to you guys. Oh, like you guys can ask me any questions. I'm here. I'm around.
Dr. Chen?
Yes.
So
Yes,
I
I
have a
can hear you.
question.
Yes.
Yeah. So are you coming to the campus every day, or?
No, actually, I'm not going to the campus at all. So yeah. But
So maybe if I want to talk with you, then maybe I need to set a time for office
Yes,
hours,
yes. I
something like
guess
that?
it's that way. Like now, so you can, yeah, you can set up a time. Like I pretty much like I don't know how what's your working time. So I typically work afternoon. Like so so any time like yeah, afternoon. Most of the time yeah, I'm available.
So you're working at home?
Yes.
Okay, I see.
Okay, I guess we will continue. So we have introduced a mean, actually not introduced, really a review for mean and variance. And so I guess next thing I'd like to talk about base rules. I think like most of you know what is that also. Like for base rule is like we have the conditional probability. If we have two random variable, let's say so MATLAB or Python. I think this is Python. You see that's NumPy there. Oh, I think I obviously I get a correct answer basically. So I don't know whether I need to go through that. Probably not. So you guys it's pretty simple, right? This maybe I just a couple words. Like so the variance here, like you can just use this equation directly. So I have x, the expectation of x beyond the original is 2 here. So so then I have take x values. When it's 1, then 1 minus 2 is minus 1. And when it's 2, it's equal to 0. When it's 3, it's 1. When it's like 4, it's like 2. So therefore expectation of this guy is like minus 1 times 0.4 plus like 0 times 0.3 plus 1 times 0.2 plus 2 times 0.1. Yeah. And that one is just equal to 1. And Yeah, I see you guys are using NumPy to do that, but honestly, it's really quite overkill. But anyway, that's nice. So, okay, let me continue again. Like, so we talking about, I'm saying that we try to look into base rule. So if I have like some random variables, and then like, yes, you need to import NumPy as MP. Yeah. And so I continue? Like, you guys are settled with the question now? Like, are you done? Like, or like, so. Okay, I guess I will continue then. So okay. For base rule, basically say if I have, let's say, x and y, two random variable, right? And let's say I have some outcome like small x and small y, then probability of x given y, that given y is equal, maybe I write like that. So what it means here is basically saying that what's the probability that x is equal to small x given y is equal to small y, that is equal to the probability of xy, yeah, I guess xy over probability y. So that is a probability, or like I can write probability x is equal to x, y equal to y over probability y equal to y. So that's base rule, and I'm sure you've seen that before, and it's quite easy to kind of like argue why this is true as well. Maybe I'll give an example and also like as an exercise. So let me give a numerical example as follows. Let's say I have like random variable w is like whether the ground, ground is wet. Basically refer to ground is wet. Let's say tomorrow maybe ground is wet. Not w, and I mean this is a lot. I'm not sure you see this symbol before. This in logic it means like lot w is a, so this is the negation of w. So it's like ground is not wet, let's say. And then maybe I have this sprinkler. It's like event is basically the sprinkler is on. And I have not as basically sprinkler is not on. And I have, let's say, rain. Let's say if it rain, then rain. And then I have negation of rain, not rain, let's say. So I have these events here. They are all kind of like random events. Let's say this is like a prediction for future. Let's say like whether tomorrow, whether the ground outside will be wet, or like whether the sprinkler is actually on like in the morning, or like whether it rains in the morning. And let's say I have some probability distribution. I would just put it in a table. Basically, I have like S and not S, sprinkler on, not on, and also like, of course, this is kind of weird. Like sprinkler on is like as a random event. You can think of like maybe the sprinkler is broken. Like sometimes it's on, sometimes it's not on, something like that. And I just put up this number I just made up like last night. So and let's say W like that, not W like that, S not S, not now, and 0.05, let's say 0.1 and 0.4. So based on that, maybe I ask you a couple of questions then. Like, what's the probability that it actually rain And if the ground is wet, but the sprinkler is not on. So maybe, okay, maybe I'll give you again like 2 minutes or something, I don't know. So this is a question 3, let's say. Well, this is quick. Yeah, I didn't look at that carefully, maybe this is it. So since so okay, the problem is that you guys maybe want to send perfectly to me first. Like when you send to everyone, then like is I don't know that that's meaning for others to answer. But I guess it's better like for other guys to answer anyway. So can you? Okay. Okay, be careful what I'm writing here in the tables. Actually, from what I'm writing down here, maybe the first thing even I don't have legend here, I don't have a title. I mean, put a title here for my table. But if you see, like I added all the number here, add sum up to 1. So I have like 0.2 plus 0.1 plus 0.1 plus 0.1 is what? Like 0.5, right? And then plus 0.4 is 0.9, and then plus 2, 0.05 is 1. So this number all add up to 1. So therefore, this is actually the joint probability. Know that. So so okay, then like maybe you want to like double check your answer. Does it make sense or not? I'll just say you guys answer is not right. So you want to double check. Note that like what we just talked here, the definition, or like you can say definition, but really what's conditional probability is given by this, like be very careful, it's given by this guy here. So now I given this, like conditional probability of x given y is like px. Okay, I have someone have different answer, probably it's correct. I don't know, I didn't check. So
Professor?
yes.
We should have the individual probability distribution as well. I think, or we don't need that. Because if we are going to use Bayes' theorem, then in the denominator, we have the one probability as well.
Oh, okay. Know that like we mentioned this, but not because I kind of like I didn't really give a, I mean, emphasize that. But remember that like we have something like this, right? You can compute the marginal probability by summing up to doing some marginalization. Yeah.
Okay. Sorry.
Yes. No, not at all. So let me go back to this one so everyone can see that. So I see someone get some right answer now. So do you guys agree? I'm not sure it's right. Actually, I didn't check the number, but it probably looked a bit more correct than 0.1. Okay, you guys are. Oh, so I give a bit more time, right? So I guess okay, maybe I'll continue. I assume like you guys more or less have finished. So Joe is white, but I don't know where you get that point 3 there. That is kind of mysterious for me actually. Point 3 over point 0.45 for Joe. Samuel is white, so that one is would be my solution basically. So so if know that these are the joint probability, so this will be equal to probability of R W M naught S over probability of W M naught S. So what is probability R W M naught S? What's the probability to be rainy and wet and not sprinkler not on? That would be 0.1. That's most of you guys got at the beginning. But remember, we need to normalize by this guy here. Otherwise, it would be just the joint probability. And then like this will be PW not S, then as Kanju also asked like that, you yeah, that would be like 0.1 plus 0.05 as I almost said, right? So that will be the probability. This is just 0.1 plus 0.05, so therefore it's 0.1 over 0.15, so therefore like 0.6. Actually, the number is not correct was also, right? So if I change this, for example, like I change this to consider probability of what's the probability to be raining, and I have W but S instead. What do I have? That would be, see, like that would be equal to what? Rain, sprinkle on MS. This is a 0.2 here over WMS. WMS is like this one is a point, but actually it's the same number here. I didn't make up the number very well, honestly. That's I don't make up the number. If I make up the number better, like this probability should be smaller, preferably. But I just arbitrarily make up the number last night, so therefore, you can imagine that if I do fall, if the ground wet, that there would be some suggestion that may have rain, right? And then if also the sprinkler is not on, this sometimes are known as like what do they call that? I suddenly forgot. Okay, it doesn't matter. So, but if I expect that like, if the sprinkler is not on, that then this is more likely to rain than like when the sprinkler is on, right? So, but the number, okay, next time I probably should set the number a little bit back, but then at least this should be bigger than this guy. I mean, this should be bigger than this guy. So then the number will make more sense. So, but anyway, I guess hopefully this, you guys see like, okay, have an exercise for base rule and also this conditional probability. And okay, and then another thing, like since we introduced some kind of conditional probability and like multivariable cases, I mean multivariant cases, then we can talk about like independent dependence or like conditional independence. So we say like two random variable like X and Y. So two random variable X and Y are independent. I guess I'm quite sure you guys see this before. Then I have Pxy is equal to Pxx. P, Y, Y, something like that. So they can be decomposed as a product if the joint probability can be decomposed as a product. Apparently, you see in my example here, like the variables are not independent. For example, like if I see like PSW, let's say PSW, right? Let me just write this. PSW, the sprinkle on and wax, let's say that is equal to P-form theory, that's equal to point 3. But PS itself is what? PS itself is equal to what? This is equal to this one plus this one plus this one plus this one, right? Is equal to 0.4. And PW is equal to all this sum together. So it's equal to 0.45, something like. And of course, like this is 0.3 is not equal to the product of like 0.4 with 0.45. So so therefore, like S and W are not independent. Sometimes we use a notation like that. So when we say S and W are independent, we have this like perpendicular, or something like with this perpendicular label symbol. Or like sometimes we put 2 stroke there. So and we also have like conditionally independent. So if I say XY are conditionally independent, given another variable Z, let's say, then I will have like Px, Y, X, Y given Z is equal to Px given Z. Wait a second, I should put a Z here. Px given Z, X given Z, Y given Z. Okay, Y given Z, something like that. So it's like kind of very similar definition if you look at that. But be very careful. Basically, everyone will make this mistake first time they look at these 2 definitions. I see everyone make this mistake, like including myself and all my students, basically. And so therefore, like I would like to like emphasize a little bit here. It's like you don't have a causal relationship like for like random variable to be independent and conditional that 2 random variable are conditionally independent given some random variable. So basically we don't have something like X and Y are independent, then say imply like X and Y are conditionally independent given Z. So this is not true. And also this other way one is not true as well. So we don't have like say 2 random variable conditionally independent, then like X and Y are independent. So let's say like, let me give a counterexample for each of these. So say if I have like I flip a coin, let's say I flip a coin, like if I got a hat, then I map to a number 0, let's say. And if I got a tail, map it to a number 1. So right. So basically this is like for hats, it is for tail, right? And I flip the coin again, let's say I have this and a different coin, or like the same coin, but I flip it at a different time, the next time. Then I have like, again, I show if like I got a hat and 1 got a tail. So apparently these 2 are independent events, right? I have X is independent of Y. But let's say if I define a random variable Z is equal to just XOR of Y, let's say. Then, or like this is like bitwise sum or like whatever right, you call this. So then apparently like if I have C is equal to X XOR Y, then I will have X is also like equal to Z XOR Y, right? So because I do an XOR operation on both sides, Y XOR Y itself got cancelled, so therefore I will have this equal to this again. But then like immediately you see that I cannot have X conditionally independent given, I mean, independent of Y given Z, because given Z here, X and Y is very much dependent, right? Because X, given this Z here, I can evaluate X directly from Y. So therefore, no way that like X and Y are independent. So, so I don't know whether this example is clear. So just let me know if like this is not clear. But basically, like I start with X and Y, they're independent, but if I introduce this Z as a X XOR of Y, then if I also include this Z here, then X and Y can no way to be independent. Because when we say X, two random variables are independent, that means that like given one random variable, there's no way I can predict the other random variable. Right? But here, if I give them Z here, I give them Y, then I can predict X precisely. Therefore, no way X and Y are conditionally independent given Z. And so this is an example of this. And we can also create a similar example like in this way. For example, like you can think of like actually what is conditionally independent. Also, like this is actually implied that there's some Markov chain here. If you guys remember what is Markov chain, so it's I have a Markov relationship like that. It's basically saying that like Y given Z then will not depend on X, something like that. So you can quite easy to show these two conditions equivalent. So this guy, the condition is P X given Z. Oh, okay, that's something. Okay. This again, I said like the definition of conditionally independent of X and Y given Z is like Px Y given Z is equal to Px given Z, Py given Z, right? And this one here, that actually, this essentially implies that Py given X Z is just equal to Py given Z. So it means that like, if I am given random variable, both X and Z here, maybe I put a comma here, but it doesn't matter. It doesn't mean X times Z is like two random variables like X and Z. So if I give an X and Z here, and I consider Y here, it's the same as I'm just given Z here. So that's basically the Markov property, right? So if you think of like previous events, right, it only depends on yesterday events. Like for example, if I have very idealized like prediction like of stock market model or something like that, it's a Markov model in the sense that of course this is totally incorrect in that case. Maybe it's better like for weather model, maybe like that given like yesterday's weather condition, I don't need to care about like in terms of predicting like today's weather. I don't need to care about like any days before yesterday. So it will be like have a model like that. If we satisfy this, so then I will have a Markov condition. And these two, it's the same. And you can very easy to verify that. Let's see if I can do it quickly. Let's see. Because this actually, by base rule, you can use base rule and to show that Pxy given Z is equal to Px given Z, Py given X Z here. So actually, this is like always quite useful to use like the base rule as like a chain rule. I would say like when you have a bunch of random variables, let's say PAB, let's say PAB C given D, let's say. So this is a PA first given D, then PB given A and D, and then times PC given A and B and D, let's say. Yeah. And this is a, okay, this is always true. It doesn't depend on like whether like this XYZ satisfy any kind of condition. This is like always true basically. This is just Bayes rule. You can expand that. Like you can show that using Bayes rule, because I won't go into that, like, because you can go home and do an exercise, because this is like B A B C D over P D or something like that. Then you play around and go do some algebra, then you can show like this is true. So then like with this is equal to this guy, right? This is like,
Dr. Sam?
yes.
So this holds even if A, B, C, and D are not independent?
No, they're not independent. Be careful. Like if they are independent, then you may have something like extra. For example, like if you have A, B, C are conditionally independent, then this can be equal to PA given D, PB given D, and PC given D, something like that. And I write this is like absolutely general. So you can go back home and derive that using Bayes rule. So this is I just apply Bayes rule multiple times. So then have something like a chain rule kind of property. Something like you can see like each time like I have this, first consider A, I have A given D, then I have B, consider all the previous random variable A and B. So the way you think of that is like the probability of A, B, and C. Okay, I can consider one variable at a time. Right? Given D, I have considered the first variable. I given A equal to small a here, and given D equal to small d here. Now, when I consider next random variable, B here. So because A is already given to be this small a, right? So I need to include that in my condition there. So then I can go to the next variable like C. Now my next variable should, given the condition, like for all the conditions that I considered earlier, that would be like D, A, and B. So like this. And this is very, very useful. Like you should kind of like remember that. I mean, it's very easy to remember. And it's quite easy to show it also, but I guess I will skip it here. And it may be a little bit tedious. But with that, it's very useful to show this, that like when you have, say, this, oh wait, where am I? Okay. Yes, I have this, let's say this have to be conditional independence, X, Y are conditionally independent given Z. So I have this condition is satisfied, right? But also like this is always true by just Bayes rule. So, but then you look at, let's see, then I compare this guy with this guy here, right? So then therefore like when it's conditionally independent, these two terms will be the same. That means that Py given xz is equal to Py given z. So that's exactly this condition here, the Markov condition here. So that means that like whenever you say something like x and y are conditionally independent given z, it also means that like this Markov condition is basically like x, z, and y form a Markov chain. So again, like this is something quite important. It's very good to know. So but I as I said, it's very easy to derive condition like that. You just want to remember this kind of chain rule, like PABC is equal to PA times PB given A and PC given AB. And it's actually very natural also, right? You can deal with one variable at a time, but remember, like when you consider the next variables, you need to make sure the last condition is given. I mean, the last variable should be given as a condition. And of course, like for the special case here, if I just two variables, right? If I have, actually, I can even like, I think it's not hard to show a little bit, like not completely, not the most general case, but for example, like for PAB, right? By Bayes rule, I already know it's equal to PA times PB given A, right? So now if I have PA A, B, C. So this is just base rule. This is basically base rule. And then I have P, A, B, C will be like P, A, P, B given, wait a sec, oh, sorry. Yeah, I shouldn't write like this. It will be like P, P, B, C, and P, B, C given A, right? I can consider B, C as one variable at a time. I mean, one variable, right? And then P, B, C, wait a sec. Oh, okay. This is wrong because this is wrong. I'm sorry. Okay. This is PA given BC. Yeah. Okay. This is base rule. PA BC is a PBC and PA times PA given BC. And then at BC I can use base rule again. So it will be PC and P B given C and PA given BC, right? So it's a little bit different format, but again, like you can, of course, you can continue to do that. Like so, therefore, like you have like something like a chain rule here for any joint probability you can write in this form. And also, if you put in a condition, you can basically very easy to show because when you have a condition, it means that you just over a conditional over a marginal probability for both right hand side and left hand side. So you should end up the same thing. So but anyway, so let's see. That's base rule independence. Okay, actually I didn't finish my argument here. What I'm saying, like, be very careful. Like when you have something that's like independence, it doesn't necessarily mean that it's like conditionally independence. I just give an example like that. But also, like if you have something that's conditionally independence, it doesn't mean that it's independence as well. So let me complete my example here. So as I said, like if something is conditionally independent, another way to look at that is like they form a chain rule. So I have x, y, and z. Let's say it's like x, y are conditionally independent given z. So that means I have chain rule like x, z, y, right? So one possibility that it can happen, like maybe if you're a communication engineer, maybe you can think of like this is let's see. Maybe X is some message. Okay, I'll send the message. Maybe this. Let's see. It's okay. I guess X. I use X as a message or whatever. Or maybe like X is like something you transmit through a channel. So this is like X input to a channel. So like you go for a channel, then like Z is like output of a channel, let's say. And then like you have Y is like a decoded message, So let's say the decoded message is use some like randomized algorithm. So like Y is like also random variable, like somehow like so. But anyway, like if you have a structure like that, like then naturally you have a Markov property. When you try to decode the message, given the output of channel, it really depends nothing on the input of the channel, right? I'm not sure this is a good example though. Maybe this sounds illogical. Let me give a more concrete example that have to be correct. So let's say I have maybe each time I add okay, I use a similar example as before. Let's say I have X is just a binary random number. So I have like 0 and 1 with like equal probability, like 1/2 and 1/2. And then it go through a BSC channel, so a binary symmetric channel. So if I have some probability get flipped, so I get C here, let's say I have probability like P it got like 0 flip to 1, and then here also with probability P from 1 flip to 0. So let's say this probability is like 0.1, let's say. So meaning that again, like if my X is equal to 0, that have like probability like 0.1 that I will have Z equal to 1. So this is like the probability 0.1, let's say. And then let's say I have Y, go for another binary symmetric channel. Let's say again, I get Y here. So this again is like 0.1. Let's say P is equal to that. So now this one apparently is conditionally independent. Give X and Y conditionally independent given Z. So if I try to, if I don't know Y, I might try to predict Y. As long as given Z, actually I don't care about what X is, right? It doesn't help my decoding. I mean, it doesn't help my estimation of Y here. And so that exactly have this kind of like P Y given Z X is equal to P Y given Z. So therefore I have the conditional independence of X and Y given Z here. But on the other hand, X and Y apparently are not independent, right? So because when I combine that, like essentially it's just like X and Y is like X passing through a binary symmetric channel with like probability of like what probability, I don't know, with some probability Q, right? It's combining this binary symmetric channel. I think the Q is approximately 0.2 or something like that, close to that. So therefore like X and Y is no way to be independent. Even though like X and Y are independent given Z. So yeah, therefore know that like again, like these two conditions, like don't assume like if you have one of them, then you automatically have the other one. Okay, I need to spend a little bit more time than I thought, but I guess it's okay. I guess maybe then I leave a interesting problem open-ended for you guys to think about. So I think some of you may have heard of that before and saw that before, but maybe some of you are new to some of you guys. This is known as the Monty Hall puzzle. This is quite interesting because I don't know, like you guys know Adolf, right? A very famous mathematician. And even he made mistake for this puzzle. So and this is a very controversial puzzle in the sense like a genius, I don't know, a genius woman, he gave a solution that is not it's basically just genius, like IQ like 180 or something like that. Like he gave a solution that without any knowledge of probability or something like that, like you just say, okay, the answer has to be like that. And then many people are not agree with that, and they just say it's wrong, and then many of them are PhD and they are all wrong. They were all wrong, including adults. Actually, adults made a mistake for that one. This one also. So basically, the puzzle is like this. So it's a game show. So you have a host. So you have a host, and you have a guest, right? And you have 3 doors here, and you have some prize, maybe cash prize, behind one of the doors. Only one of the doors, like not all 3 doors, one of the doors. So what the game is like I have a guest here. The first one, the guest will decide like pick a door. So he pick a door. Let's say he pick this door. Let's say this is guest, pick this door here. And then once he pick the door, what the host he'll randomly, or not randomly, he'll pick the door that does not have the prize and not the guest door, the door that picked by the guest. So let's say like for the host here, so the guest first pick this door, then the host will pick the door again, like without the prize and also not picked by the guest. So in this case, can only be this door here. And then he will open this door and let me enjoy it, open it. So, and reveal that, okay, there's nothing inside, so nothing. Now, then the host will ask the guest, like, okay, do you want to change your mind? I mean, like, change your mind meaning that, okay, originally he picked this one, and the host like open the other door, right? Then the only one door he can switch to. Basically, like the host will ask him like whether you want to switch the remaining door. If the question is like, do the guest have higher chance of winning by switching to the other door? Oh, maybe this is fun. Maybe I'll also like leave you guys like, okay, try. Do you want to spend like, I don't know, 5 minutes or something, like think a little bit about it, and then maybe let you. And also like one thing I want to do is I show. Okay, my cat is like keep yelling. So why this probabilistic programming is helpful, like, because for things like that can be not quite intuitive. Like it's easy to make mistake. And in this case, I don't know whether I have enough time today, but maybe next time I can just write a short program. May not be using like a real using the packages like common packages in probabilistic programming. Yes, the host will never open the door with price. Like if open the door with price, then it doesn't make sense. So basically, okay, this is one case, right? The other case, let's say maybe the guest doesn't pick this door, like maybe pick this one, right? At the first one, he picked this door here. Then the host have some choice. Like he can either open this door, like open this door. Maybe open this one, maybe he still open this one. Now again, like host will ask the guest whether you want to switch. So the question is always like, do the guests will have a higher chance of winning by switching door? This is the Monty Hall thing. I'll try to look for that, because I'm sure if you go online, there's lots of like different discussion. I'll try to think a little bit like yourself as like what do you think, like how you. I have like still 15 minutes left. I guess I'll just give you some time, and maybe 5-10 minutes to think a little bit, maybe discuss among yourself even. Like what do you think, and then maybe you can again I send a solution. Yeah, like not exactly, maybe just your current guess. Like you don't need to answer. I mean, like at this moment, maybe you don't need to you don't need to give the entire solution, like the procedure, how you ended up the solution. Maybe it's even interesting, just check your intuition. Like what do you think? Like what do you think? Like if you have a situation like that, what do you think? Do I get, if I am the guest, if you are the guest, will you switch the door? Like will you try to intuitively, by gut feeling, do you think you should switch door?
No, I think so.
Okay, someone say yes, but okay. Someone is intuition is right, but the solution may be incorrect. So I don't know, okay, let me give a little bit more time for you guys, and maybe 2-3 minutes at least, like to think about that. But the question is clear, right? The problem, like problem solver is clear, right? Actually, I have like 10 minutes. I guess maybe I still have time to do some simulation. But I guess I'll give you guys 1 more minute or something. So I think the class is end 50, right? So I guess we have a little bit time to do some exercise. So let me see, like programming things. Okay, let me see. I have this a little bit complicated for me to, let's see. Okay, somehow I did some simulation, yes. But I'm not sure the simulation is correct, actually. Yeah, at least I don't quite. But okay, maybe we go through that together. Let's see. So okay, let me quickly do this together. So hopefully, but I try to move you guys chat to my another screen, so it's kind of complicated. How do I do this? It's pretty annoying. Machine chat. Okay, let me okay, let me. How do I where's it? Yeah. Oops, but I only have. It looks like I only have 4 minutes, 5 minutes, but I guess it's enough. So let me just use Python. I maybe just quickly. Oh, by the way, I assume that many of you guys are familiar with like Python, right? So I guess I don't need to. Okay. So let me use NumPy. So I'm not going to use like anything fancy here. So I just use NumPy a bit. I do like a 10,000 or 1,000 simulation here, like 10,000, let's say. So I will just call D is like the door, the actual price. So it will, the door with actual, so this will be, the door can be like 0, 1, and 2, right? So this is a random door here. And then let's say I call it O is the original pick. Let's say it's like, also it can be like 0, 1, and 2, right? So let's say I have that. And then I just create a function to determine like what the host will pick. Let's say I have the D and O will be what for each simulation each time, like what door the actual price like is behind, and then what's the guess pick like each time. And then I'll just make a sequence like this is a host pick. I call it H here, and the size here will be just have the same size as my D here. So it's initially I will set it to zeros. Then I just look through that. Okay, this is not the best way to write it. I guess I can vectorize that, but for simplicity, easy to understand, I just write that for loop here. So I look for like each of the simulation, like each time. So 10,000, is that 10,000? Or yeah, 10,000 to 100,000 times. So that's a couple cases, right? So first case, if the guess, basically if the guess pick the door is the same as the actual door, then the host have like basically some choice to pick. So it can pick like there's 2 doors, like 2 different choices. And the choices will be like, I use a set difference here. So will be like amount like 0, 1, 2, that's all the doors here. Basically besides the door that basically the guess pick, like that's basically the other doors. So for example, if like OI is equal to 0, then the set difference will say like, give me like 1 or 2. And then out of this list, I will just randomly pick one of them, right? So then I can like pick, let's say a random index. Again, I use one integer again. But I have the integer either 0 or 1. So this will pick either, for example, if my OI is equal to 0, then I'll either get door 1, like if my when int returns 0, or like I will return door 2 if my when int is equal to 1. So then for the other case, that would be even easier. So if like the 2 door is not the same, then the host can just pick the other doors, right? So I can simply like, because I have the door numbers are 0, 1, and 2, I can just like add them together and subtract each of the doors. So it will be give me the remaining door, right? So I can have 0 plus 1 plus 2, I will get 3 here, minus DI, basically the true door, and then like minus OI is the door the user's pick, and then that will be my function to get the host pick. So then I can just have, let's see. Then let me do some count here. Let's say I call it original count. It's basically like the counts that taking the original is actually get the right door. That would be basically just counting everywhere D is equal to O, right? And this actually I need to put a 0 here because when I use like D equal to O, actually give me what should I say? It will give me tuple instead of like the value. So I need to pick the first one to get the array here, and then I just also get like how many numbers there will get a shape there, and then actually I didn't find the holes yet. I just create a function. I should have like holes is equal to, therefore equal to holes pick EMO here. So sorry, I'm a little bit over time, but I'm quickly finishing that. And so the other door will be like S. It's using the same token here, right? I would just have like the other door will be like just equal to 0 plus 1 plus 2 minus the original door plus the holes pick, right? So that will be the other door. That maybe this is like, I call it the swap or like whatever the other door. And then like the swap count will be the same thing, is equal to empty, where D is equal to S. So then I can print it out, basically the probability. So therefore win given no swap will be equal to original count over n, right? So this is a sequence. It's 1/3, as many of you guys will expect. And then probability that win given swap will be equal to swap count over n. So this is equal to 2/3. Many of you guessed correctly. Actually, I don't know whether you get the right answer like by guessing or like go for all that. Okay, but I guess I should stop here. But it's good time. I only overrun by a minute. I guess it's not too bad. But you see, like sometimes it's hard to get the right intuition, but you can program that and get the correct answer. But I guess next time I will also like go through the maybe just analytically why this is 2/3 actually, for example. And then I guess I will stop here. So you guys have any questions? And let me see if I hope I should get back this chat. So if I don't, I will be in trouble. So I don't see anyone have any questions, so I will just stop the meeting now. So I will see you guys next Wednesday then.
Dr. Chen?
Yes.
Yeah, so where can I get this recorded the lecture?
Oh, I will put online. You can go to the website also. Like if you don't remember my personal website, you can just go to Canvas. There's a link to my personal website, with the course website, and I will put the recording like in the Canada or something like that. So you can pull down and you can see the link there.
Okay, thank you.
Yeah, okay. So then if no other questions, then I'm going to stop the meeting now. Okay, see you guys next Wednesday then.
Bye. See you. Thank you. Bye.
Yeah. Bye.